Try making sense of scratched-out notes to determine how sunlight affects plant height. It is nearly impossible. To find an actual pattern, we extract those chaotic observations and arrange them into a pristine, formal table. Before we can map trends or calculate predictive equations, we have to impose structure on our numbers. Tabulation is the mandatory first step. Every formal statistical table starts with a title. This clearly establishes what the data measures, where it was collected, and when. Next are the structural labels. The row titles going down the left side are called the stub. The column headers running across the top are the caption. For our experiment, our stub tracks sunlight days, our x variable, and the caption tracks plant height, our y variable. The central grid is the body. This space strictly holds the actual quantitative observations we gathered in the field. Structuring the matrix this way prepares it for analysis. It isolates each variable so we can compare them mathematically. Tables give us exact precision, but graphs instantly reveal trends. By plotting these points on a Cartesian plane, our data forms a scatter plot. This graph clearly shows a positive correlation. More sunlight leads to taller plants. But visualization has limits. We cannot reliably guess the exact plant height for a day we haven't measured yet, like day 15. To solve for those unknown future variables, we move from drawing shapes to calculating a regression equation. Pay close attention to the notation here. Capital letters represent our raw data. The lowercase variables represent deviations from the mean. The graph proves a relationship exists. The equation calculates the exact dimensions of that relationship. To calculate the inputs for our regression equation, we expand our table. We add specific columns for the lowercase deviations, x, y, x squared, and x times y. The first computational step is finding the baseline averages for our raw inputs. We sum the capital X and capital Y columns and divide by the number of observations to find our means, known as x bar and y bar. Let's walk through the first row. We subtract the x bar mean from our raw x value to get lowercase x. Then we square it. We do the exact same subtraction for y to get lowercase y. Finally, we multiply x and y together. Now it is your turn. Pause the video and calculate the lowercase values for the next two rows on your own. Without organizing the data into these precise columns, keeping track of this sequential arithmetic would be nearly impossible. The table acts as our mathematical scaffolding. Expanding these columns yields our final totals, the sums of x squared and the xy product. Dividing the xy sum by the x squared sum provides the regression coefficient. 247 divided by 218 is 1.133. Plugging this multiplier into our equation produces a final predictive formula. Translating that algebra onto our graph, the final equation draws a line extending into unknown territory. This is the complete pipeline. Tables organize facts, graphs reveal trends, and equations predict the future.